So let us see now what is resistance and Ohm's law. Now we have already seen that electric current is a flow of electrons. Now when this electron flows, it collides with other electrons, ions, atoms within the conductor or in the path of the electron flow. Now due to these collisions, there is obstructions to the flow of electron, and this obstruction is called as resistance. So now you can easily understand that whenever the resistance is more, the path of current is slow or low, and whenever the resistance is very high, the current cannot easily pass through it. It is just like that whenever 10 or 20 students are passing through a very narrow passage, what will happen? The passage, the width of the passage is a resistance. Okay, so there is a limitation to the flow of the students, or whenever the student passing, there is a limitation. But suppose if you widen the passage, that means if you reduce the resistance, the flow is easy. So we can easily understand that whenever this resistance to the flow of electron or the electric current is low, that conductor will be called as good conductor of electricity. And obviously, whenever the resistance is very high or infinitely high, at that time, that conductor will be the bad conductor of electricity. For example, almost all the metals are good conductor of electricity, whereas the substances like wood, rubber, plastic are bad conductors of electricity. Now numerically, resistance is denoted by letter R and it is calculated by V upon I. Resistance is equal to potential difference divided by current. Now you can see that this R is directly proportional to the potential difference, and it is inversely proportional to the current. And this is the Ohm's law. The Ohm's law says that the resistance is directly proportional to the potential difference and inversely proportional to the current. Now, there is one condition in Ohm's law. Condition is, for this, the physical condition of the conductor must not change. That means the cross-section area of the conductor, the length of conductor, the temperature of conductor and material should not be changed. And so that is the Ohm's law. Because if no other resistance is applied from outside, this R for any material is constant. And so V will be is equal to R into I. So your Ohm's law states that, now by the way, what is Ohm's law? George Ohm was a German scientist who stated a law which we call as the Ohm's law, by which we calculate the resistance in any electrical circuit or the resistance of any substance. Okay, so the Ohm's law states that the potential difference is directly proportional to current. Since R is constant, we can say that V is directly proportional to I. But in the Ohm's law, there is one condition. The condition is, since the R is constant, that means the physical properties of a conductor, that means the length, cross-sectional area, temperature and material should not be changed. Let us see the Ohm's law once again. The potential difference is directly proportional to electrical current, provided the physical properties of a conductor like length, cross-section area, temperature and material remains constant. Now if we plot a graph, current on y-axis and voltage on x-axis, that means suppose if we go on increasing voltage, the current will increase, and if we go on increasing current, the voltage will increase. This graph will show you a straight line. The slope of this graph will be 1 everywhere. Now, in honor of the George Ohm, the unit for the resistance is called as ohm. So the unit of resistance is ohm. It is denoted by this symbol, this Greek letter, and it is called as ohm. Now, how will you define ohm? 1 ohm? Very simple. When the potential difference of 1 volt is applied across and current of 1 ampere is flowing through the circuit, the resistance is equal to 1 ohm. It is very simple. Again, I am telling you, please by heart the definitions word by word from your textbook. Okay? So this is about the Ohm's law. Now, before going ahead, the graph what we have seen, how will you make the arrangement? How will you arrange these? Or how will you prove that this graph is a straight line? It is very simple. Now, suppose if you have an electric circuit, let us say very simple circuit. I have one resistance here. So this is the arrangement of instruments, or this is the circuit diagram for proving the Ohm's law. What we are going to do? In this case, my power source, this battery or the cells are variable. That means we have an instrument called as the eliminator, in which you can adjust the voltage from 1.5 volt to 12 volts in parts: 1.5, 3, 4.5, 6, 7.5, 9 and 12. So what we are going to do, we are going to adjust this voltage from 1.5 to 12 gradually, and at the same time we will check what voltage is in the voltmeter and what is the current in ammeter. As your voltage goes on increasing, at a particular point, as your voltage goes on increasing, you will see that current is also going on increasing. And at this point, you will find that this graph is of the straight line. So, we will prove that is directly proportional to I, where the resistance is constant and the physical property of the material, that is the length, cross-sectional area, material and temperature, remains same. Now, from this, we are going to see what is called as the specific resistance or resistivity of any material. Now let us see what is the resistivity of a conductor. This resistivity is also called as the specific resistance of a conductor. Now, one thing I will remind you, that the resistance is depend on the length of the conductor. Okay, you must have observed that if you have a 9 volt battery or a small cell, 1.5 volt cell, and 2 wires are there which are attached to a bulb, what will happen? The bulb will glow. But when you go on increasing the length of the wire attached to the bulb, what will happen? The bulb will go on dimmer and dimmer. Okay, the brightness will be reduced. Why? Because the length of the conductor is increased, and so the resistance is increased, and so lot of current is wasted in opposing that resistance, and very small amount of current is reaching to the bulb. That means your resistance is directly proportional to the length of a conductor. Now again, let us consider that passage example. A group of students are passing through a passage. Now that passage width is low. The passage is narrow. What will happen? The students will not able to pass easily. But now suppose passage is wide. What will happen? The group of students can easily pass through the passage. That means when your cross-section area is increasing, the resistance is getting lower and lower. Now let us consider that passage example. A group of students is passing through a passage. If the passage is narrow, there will be obstacles and students cannot easily pass through the passage. But when the width of the passage is more, the passage is wide, what will happen? The group can easily pass through the passage. That means my resistance, what do you mean by the width? That is the cross section area. Okay, so my resistance is inversely proportional to the area of cross section. That means when the length increases, the resistance increases, and when the cross section area increases, the resistance decreases. It is inversely proportional. Now when I combine these two, what I will get? R is directly proportional to length upon cross section area of a conductor. To eliminate this proportional sign, I will say that I'll have to take some constant which will be rho L upon A. This constant is a characteristic of material, characteristic property of the material, which is called as specific resistance or resistivity. Okay, this is called as resistivity or specific resistance. Now this rho, value of this rho is constant and it is different for different materials. So how will you define rho? Consider that you have length of conductor is 1, cross section area is, or the length of conductor is 1 meter, cross section area is 1 meter square, and the resistance is 1 ohm. What will happen? Rho will be 1 ohm. Okay, I have considered this resistance is 1 ohm, but let us say that there can be any resistance of that particular material. Okay, what will happen? This will get eliminated, 1 get eliminated, and R will be equal to rho. So the specific resistance or the resistivity can be defined as the resistance of a conductor of unit length and unit cross section area. Again, specific resistance is the resistance of conductor of unit length and unit cross section area. Okay, now what is the unit of this rho, specific resistance? Very simple. From here we can say that rho is equal to RA upon L. R is in ohms, area is in meter square, and length in meter. So unit for the rho is ohm meter. Very simple. So you will get examples based on specific resistance also. Okay, let us see few examples based on this formulae. Now before going directly to examples, let me clear one thing. I told you that the rho is a characteristic property of any material. Okay, when the value of rho is very low, that means that particular material is a high conductor of electricity, is a conductor or is a good conductor of electricity. And when the value of this rho is very high, that will be bad conductor of electricity, or it is called as insulator. Now table 4.2 will give you the values of the rho or the resistivity value for the different metals or the different materials. I am just going to tell you the highest and lowest. Highest, that means the best conductor of electricity is silver with 1.6 into 10 raised to minus 8 ohm meters. 10 raised to minus 8, this is a very small amount. And about the glass, 10 raised to 10 to 10 raised to 14 ohm meter. The specific resistance of glass is very high. That means it is bad conductor of electricity. Now why they are given 10 to 14? That means 10 raised to 10 to 10 raised to 14. Because again it depends on what type of glass it is. Okay. So you will get the complete list. Now in this case, the silver is the best conductor of electricity, as they say. Then it comes copper, then aluminum, tungsten, nickel, all the metals are there. Then some alloys are there, constantine. Then there are some alloys, constantum, manganese, nichrome, and then insulators, glass, hard rubber, then your ebonite, diamond, paper, etc. I have just shown you the highest and lowest conductor of electricity. This is the very good conductor of electricity. This is very bad conductor of electricity. The rest you can refer to the table in your textbook. Okay. Now, I want to tell you one more thing. Whenever you handle your electrical circuits at your home, your electrical points are at very high potential and your ground, generally we call as earthing, it is at very low potential. Okay. But suppose if you take a nail and you put into the socket and switch on the button, what will happen? The circuit will get completed from your socket to nail, nail to your body, body to your ground. Okay. And you will feel the shock. To avoid this, what we do? We generally wear rubber sleepers or the plastic sleepers, or we stand on the wooden block or the wooden table. And since rubber, plastic, wood are the bad conductor of electricity, the circuit cannot get completed and you will not feel shock. But mind well, suppose you are coming directly out from the bathroom or from the rainy season. In rainy season, your sleepers are wet, or suppose that wooden block is wet. What will happen? Water is very good conductor of electricity. Water is very good conductor of electricity, and so the circuit can get completed through your body and you will feel the shock. So in this case, all these conditions in the normal conditions. Okay. You can say that glass is bad conductor of electricity if it is dry. If the glass is wet, it will carry the electric current. Okay. Let us see few examples. Examples again are very simple. Just direct substitution of formula. The first example is the resistance of a filament of a bulb is 1000 ohm. Resistance they are given is 1000 ohm. It drawing a current from a source of 230 volt. V is equal to 230 volts. We have to find out the current. How much current is flowing through it? Very simple. I is equal to V upon R. I is equal to V upon R. So I have 230 upon 1000, 0.23 amperes. Very simple. You have to just take care that your units are in the same systems. If they are given millivolts or megavolts something, you have to convert them into the volts. Okay. Let us see second example. These examples are very simple. Find the resistance of a conductor. We have to find out the resistance of a conductor through which 0.24 current is given as 0.24 amperes, current passing through it, and potential difference of 24 volt is applied. Potential difference of 24 volts is applied. What is the formula for this? R is equal to V upon I. So 24 upon 0.24, that is equal to 100 ohm. So you have to write the answer in proper way. The resistance of a material is 100 ohms. This is direct substitution of formula, nothing difficult in that. Let us see one more example. Now in this example, we have been asked to find a specific resistance. If the length of wire is 50 centimeters, third example, if length is 50 centimeters and a radius is 0.5 mm, R is equal to 0.5 mm. Find the resistivity of wire if its resistance is 30 ohms. Now the resistance they are given is 30 ohms. Very simple, direct substitution of formula. Resistivity is equal to Ra upon L. How will you solve this? Very simple, just substitute, right? No. What we want in formula, we have resistivity is equal to resistance, which is directly given, into A, that is the cross section area. Here they are given only R. So what will be cross section area? Pi R square. Pi is 3.14 into R square upon L, length, which is given 50 centimeters, right? So substitute and do it. Now one more thing you have to remember, that is these are not in SI system. They are given 50 centimeters and radius is 0.5 mm, right? So first of all we have to write those in meters. 50 into 10 raised to minus 2 meter, and here 0.5 into 10 raised to minus 3 meters. Now you can substitute. Instead of this 0.5, I can say that 5 into 10 raised to minus 4 meters, right? Now let us calculate. Now let us substitute first. 30 into area, that is 3.14 into R square, that is 5 into 10 raised to minus 4 square, divided by 50 into 10 raised to minus 2. Now can you solve this? This is simple arithmetics. I know where the people will get stuck. They will get stuck here at the exponents, right? So I will solve that for you. So it will be 30 into 3.14. 5 square is 25 into 10 raised to minus 4 square is 10 raised to minus 8, divided by 50 into 10 raised to minus 2. So you have to do all these calculations into 5, and this figure will get 10 raised to minus 6. So just calculate this, and into 10 raised to minus 6 is ohm meter. Don't forget to write the units. Please stop, pause your video and calculate this. The answer is 47.1 into 10 raised to minus 6 ohm meter. If you want, you can write shift 1 decimal point and 4.71 into 10 raised to minus 5. Okay. So let us see one more example. If a potential difference of 33 volt is applied to a device, potential difference of 33 volt is applied to the device whose resistance is 110 ohms. So R is given is 110 ohms. A potential difference, that is, the voltage is given 33 volts, R is given 110 volts. Find a current, that is, we have to find a current. Second part is, if the same current is passed through a device whose resistance is 500 ohms. Now the same current will pass, this is the R1 whose resistance is 500 ohms. How much will be the potential difference? So in the first case, V1 is 33 volts, R1 is 110 ohms. We have to find out the I. If the same I is applied, or the same current is applied with the resistance of R2, that is 500 ohms, we have to find out the V2. What will be the potential difference? So now I is equal to V upon R. So let us calculate the first case. So we have 33 upon 110. Okay. So we will have 0.3 amperes as current. Now for the second thing we have, for the second case we have 0.3 as current, voltage we have to find out, and resistance is 500. So your V will be equal to 0.3 into 500. So the voltage will be 150 volts. Again, this is a very simple example. Just you have to calculate 2 times, nothing else. Okay. So now we are going to see the resistance, more about the resistance. The resistance is in series, in parallel. Suppose if in one circuit I want low resistance, what should I do? And suppose I want a high resistance, what should I do? That we'll see in the next topic.